So let's talk about quantum numbers. Quantum numbers seem to many students to be really puzzling, and they really are kind of the same thing as the electron configurations that you learned in a previous level of chemistry, but they don't look at all the same. So we're going to talk a little bit about what they are and try to correlate them a little bit with what you may have already learned. Quantum numbers come from, this is important to know, where do they come from? They come from the Schrödinger equation. Now, the Schrödinger equation is a really complex equation. I would suggest you Google it if you're interested, and you can probably look at 6 different places and get 6 different descriptions of the equation. It's a very, very complex equation. Although it looks deceptively simple, you can reduce it down to, a couple of letters and symbols that mean a whole ton of other symbols each, and then it looks much simpler. But it can go on and on and on. It takes several days to go through all of the calculations. So we don't want to deal with that at all. But the reason I'm mentioning this is because what they pertain to is wave functions. They have to do with looking at the electron as a wave, and we're trying to describe where that wave is in space, or what that wave does. And what it ends up doing is describing kind of a volume of space, which then describes atomic orbitals. They describe, there's more than one, so I should say describe, not describes. Describe atomic orbitals. And people always look at these numbers and say, why are they such weird numbers? Why do we have such weird things? Well, it's because it comes out of an equation, and it's part of the variables in an equation, or in a version of the equation. So we're going to talk about 3 different quantum numbers, and I'm just going to abbreviate quantum numbers as capital Q and the number sign. 3 quantum numbers are going to be covered in this chapter, and chapter 7 in our textbook. And they describe the orbital that the electron is in. Then the 4th quantum number, there's actually 4. The 4th quantum number we're going to discuss in chapter 8, okay? And it actually talks about which electron we're talking about in the orbital. Each orbital can hold a maximum of 2 electrons, and so this 4th quantum number is going to tell us which electron we're talking about in each orbital. The 3 quantum numbers, though, are the ones that come from Schrödinger's equation, and so that's what we're going to talk about in this chapter. So we're really describing orbitals, not electrons at this point. Okay, which is where the electrons live. So there are 3 characteristics that we want to discuss about these orbitals. 3 characteristics. Okay, so here we are. We want to know about the distance from the nucleus. Okay, now it takes up space, so each orbital has some space that is close to the nucleus, but we're kind of looking at how far out it extends. So in a way we're talking about size, right? And this is often called the energy level. It's also called the shell, and that may be the term you're most familiar with from previous chemistry. The other thing that one other thing that we want to know is the shape of the orbital. Remember, we're discussing orbitals. The shape is going to be described as a sub-level, thinking of the energy level up above. This is the sub-level, so it's a portion of that energy level up above. Or we can call it the sub-shell if we're talking about shells up above. They're completely interchangeable terms. And the shape is also talking about what you may remember from a previous chemistry experience as the S, P, D, or F subshells, and those are sets of orbitals. And in other words, there's several p orbitals that make up that p subshell. Okay, so sets of orbitals. we want to know what the shape of those orbitals are, and each kind has a different number in its group, in its set. The other third thing we want to know, so now we know how far away we are from the nucleus, what the shape of the orbital is. We want to know what direction the orbital is pointing. So orientation in space, or direction in space. Some people don't like that word orientation. They're like, what does that mean? It kind of means what direction is it pointing. Is it along the x-axis, along the y-axis, along the z-axis? Is it kind of laying at an angle in between the x and the y-axis? Where is it in space? So that tells us which specific orbital we're dealing with out of that set. Okay? The set above, which specific orbital in the set or group of orbitals in the subshell. So the first one that I listed talks about the energy level or shell. The second one gives us the sublevel or the subshell, and the third one tells us exactly which orbital we mean. So as we go from the first one to the second to the third, we are narrowing down. There's more electrons in a shell than there is in a subshell, and there's more in a subshell than there is in an orbital. And since we're not really talking about electrons yet, we can say how many orbitals are there, or orbital is our smallest thing we're really talking about today. So how many orbitals are in a subshell, and then how many subshells are in a shell. So as we go from orbital to subshell to shell, we're getting larger groups. So these three characteristics each have a value, and the letter, the variable for these are n, L, and we usually write it as a lowercase scripty l. These are all lowercase letters, lowercase n, lowercase l. And if we put it as a as not a scripty l, then it's kind of hard to keep it from being confused with a number 1. And so that's why we use that scripty l. And then we want an m, but this m has a subscript of an l because it's dealing with the l up above. So this is m sub l. We have n, l, and m sub l. And then besides this, they each have a special name. So let's put that in too. The first one is the principal quantum number. Principal quantum number. Okay? That's the n, because it's the main thing that differentiates. The amount of energy it has varies whether you're in an SPD or F, depending on whether you're on a hydrogen atom or not. If you're on a hydrogen atom, they're all the same. But any other atom, they vary in energy. But the principal quantum number is the big difference in energy between these guys. So it's the main event. Then we have the angular quantum number. And angular has to do kind of with shape, you know, where it goes in space. And then magnetic, the M in the M sub L stands for the magnetic quantum number, which if it's oriented one direction, it'll have different magnetic properties than if it's oriented another. You know that from even handling magnets, that if you turn them, they're acting a little differently. So there are the names. The principal quantum number, the angular quantum number, and the magnetic quantum number correspond to n,